So thanks a lot for inviting me. It's great to be here and enjoyed the talk so far, and I'm highly looking forward to the rest of them. And today I want to talk about a recent project that we did in the lab, which talks about the stability of memory with underlying unstable elements. And people who did the work, it's Lee Sussman is a grad student in the lab who's here as well, and Nama Brenner, a collaborator at the Technion. Okay, so what is the talk all about? And the basic issue is memory and synaptic plasticity. And the question that people have been thinking about for quite a while now, so decades and centuries, is how do we remember past events? And the sort of common way to think about it is that when we experience certain events, they give rise to neural activity. Neural activity, in turn, causes synaptic plasticity. And then the synaptic structure that was modified by this activity, that is what encodes memory. And when later we want to recall that memory, we can use some external cue to recall an activity pattern due to this modified synaptic structure. This is sort of the basic concept of how memory works, the textbook account. And recently, people have been actually been able to measure these things in a much more convincing manner than in the past. And I'm going to focus on the use of spines, dendritic spines, as reporters. And one paper, for instance, in 2009, they trained mice to pick up seeds. So they had like a reaching task that required some fine motor learning. And then they noticed that when the animals performed this task successfully, so some managed to learn this and others did not. And the ones that did, they could monitor the formation and elimination of dendritic spines in the motor cortex and show that A, there is more formation quite rapidly after learning, and B, the amount of spine formation is correlated to the success, to the behavioral success. So this is a clear correlate of behavior and modification of synapses. Furthermore, in more recent work from the Kasai group, they were able to manipulate this. So if the storage, so this only shows a correlation, but now this is more of a causative manipulation, because here what they did is that they could mark the spines that were modified due to learning, and then using optogenetics inhibit these specific spines. And then what they saw is that basically they had two different motor tasks, a rotor rod and a beam task. And the spines that were modified due to one task, interfering with these spines only interfered with this target task and did not interfere with the control task. So this shows that that the spines really are a selective storage of this memory. It's not just that you impair all of motor activity, but it's a very selective modification. So these results and a vast literature apart from these indicate that this basic textbook account makes sense. So it seems like we know that events influence our neural activity. We know that neural activity changes synapses, and we know that synapses are correlated and causative for memory. And there is one point here that has received less attention, again, in recent years has received more, but still relatively less attention, which is a concept known as synaptic tenacity. And this basically looks at the flip side. So if there is neural activity, then synapses should change. But if there is no neural activity, then we expect synapses not to change. Otherwise, we'll have sort of false memories or we'll erode the existing memories. And when you think of how, in a molecular sense, you could have stable synapses, it actually seems quite remarkable that it's even possible, because a synapse is not this, it's not a sculpture made of stone that you chip a part of it and then it stays there. It's a multitude of molecules that each has, and proteins that have very short half-lives, from hours to days. And it's not clear how this complex machinery can maintain a stable value for prolonged times as we have lifelong memories. And actually, when you look at the exact same two papers that I just showed you, so this is the one showing that training has more new spines. Here there is no elimination. After a couple of days, you also see different elimination. But note here that this is the control. So yes, 10% of this formation of spines in the training, but also 5% in the no training case, right? And also here. So yes, in the trained, you see there's more enlarged and there's significant differences, but this is also significantly different from 0. So even if we don't have activity or learning, we still have plasticity. And this was shown, for instance, in data from Noam Ziv lab in the Technion, that even if you inhibit activity, so this is done in cultures with TTX, they can look at the individual spines, and then what you see is some spines disappear and others are formed, as we saw before. But also, if you only limit yourself to the spines that did not vanish or appear, but you look at the fluorescence of the spines that existed throughout the experiment, then you see that they vary quite a lot. And again, this is in the absence of electrical activity. And you see there's quite large fluctuations. Now, in this Ziv lab, they also tried to estimate, again, in a very rough manner, how much of these variations are due to activity-dependent changes and how much are due to just spontaneous or activity-independent changes. And they got a very rough estimate of that it's, let's say there's, let's say 60-40 or so proportion. So a very large component of synaptic plasticity is activity independent. And that sort of raises the question, so how can memory traces remain stable over time when the underlying substrate that should maintain them stable is itself unstable? Now, of course, we're not the first to consider this. Several recent reviews and quite a lot of work from Jonathan Levenstein here discussed this apparent problem and possible ways to mitigate it. And the basic, basic solution is not that magical. We say, well, something is stable, right? Behaviorally, we see that there is memory, so obviously something is stable. But maybe it's just not that size of the individual spine that we monitor. Okay, maybe maybe if we look at strong connections, they don't fluctuate. Or maybe if we look at inhibitory neurons, they fluctuate less, which is actually the case. And work from Gianluigi Mongillo and Jonathan showed why this could be an explanation for stability of memory. It's also possible that when you look at individual spines, they are not, in a sense, a functional, the functional unit. Because if you think of the connection between two neurons, then in most cases, there is more than one spine or more than one synapse connecting two neurons. So it's possible that these fluctuations sort of average out when you consider a single connection between neurons. It's also possible that while the individual synapses fluctuate, or even the individual connections fluctuate, something at the network level is stable. And there have been several suggestions about what this something might be. And the basic concept is that you have a very high dimensional system. The network is a very rich, has a very rich activity space and very rich synaptic space. So it could be that the functional directions are only span a small space of the possible connections. And there's some orthogonal component that you can fluctuate about and nothing will happen. And what I want to discuss today is something that is in this network level. It is somewhat analogous to other suggestions, but the motivation is different, and I think the conclusions are different, and I'll be happy to hear your thoughts about this. So, network level. Here's a network, and as Christian just said, these are rate neurons that have no biological aspirations to them. And these are recurrently connected neurons, and they receive some input. And the idea will be to provide an event, which will be some activity pattern, that will change the connectivity of these neurons. There will be also activity-independent fluctuations, and later we will see whether we can recall the memory. That's it. So we need neural activity and connectivity to co-evolve. So we'll have xi will be the activity of the neurons, and wij will be the weights of the synapses, and both of them will co-vary. Or you also have subtitles for those who need them. So x is the activity of the neurons, w is the synaptic matrix, there's going to be some nonlinearity, and the input. And now the crucial part. Synapses also change, and synapses change due to two things. One is the learning, the sort of the classical thing that we always think about when we think of memory, activity-dependent modifications. If we want the input to somehow embed a memory, we should have activity-dependent plasticity. But in agreement with all the data I showed you before, there should be also an activity-independent component. And basically, we want to understand the effect of this component on the entire process. So what is this fluctuation component? Well, activity-independent noise. So basically, every synapse will just have some random diffusion, random noise is going to be added to it, which sort of, is the simplest thing you can think of. Now, in a sense, already here we have a problem, because if that's all we have, if synapses just have an activity-independent term that always adds noise on top of the current state, that will diverge. Because if you wait long enough and you just add more and more and more and more noise, then eventually you have like a distribution that is wider and wider and wider. And then some synapses will have huge weights. And so if nothing controls this somehow, it will just diverge. But of course, that's true in general of neural activity. Many things can diverge, and that's why people suggested that in biology in general, and in neural circuits in particular, there are homeostatic mechanisms. They are there in all possible places in biology. You always have things that control and that make sure that relevant variables are in reasonable ranges and nothing explodes. And basically what homeostatic mechanisms need to do is to stabilize the system, to make sure things don't explode. And most of what I will talk about is just the consequence of this. So if I have activity-independent noise to the synapses, and I have some homeostatic mechanism, what is the effect on memory? And to do that, I will take roughly 2 minutes for a short dynamical system course, because we'll need a concept from here. Okay, dynamical systems 101. The state of a system X determines the state of the system an instant later. Or another way, the change of X is determined by X, which means that if X is over here, the change is positive, so X will move to the right. And here X will move to the left, and to the right, and to the left, which means that if you look at this point over here, it is a stable fixed point because you are drawn to it. And if you look at this point here, it is an unstable fixed point. And you can also notice that the slope is negative over here and positive over there. So that's it. You just saved your semester. Negative slope, stable. Positive slope, unstable. And that's it. Only problem, this is for a one-dimensional thing, and we think of high-dimensional systems. So if we have, let's say, a 100-dimensional system, like a neural network, then instead of having one slope, we now have 100 eigenvalues, which is the same, just in German. And then these will be, some positive, some negative. And if we want stability, again, we need negative. But we need all of them to be negative. Actually, there's a bit more to it. Once you have this high-dimensional system, these numbers are no longer nice and arranged on this nice line. They can also be imaginary. Okay, so eigenvalues can have both a real component and an imaginary component. But still, it's okay. We don't care about the imaginary part. If you want stability, all we need is negative, stable, positive, unstable. All we care is the real part of these eigenvalues. Okay, so that's the conclusion of dynamical systems. You have eigenvalues. If all of them are on the left, we're okay, things are stable. So, back to the question. We have activity-independent noise that will diverge if nothing stops it. We have homeostatic mechanism that should stop it. It needs to stabilize. But we just learned that stability means keeping things on the real part, on the left of the real part, which means it is necessary to control the real part of the eigenvalues. What about the imaginary part? It can do whatever it wants, right? So the imaginary part is less constrained. So if you were to store information somewhere in these eigenvalues, actually the imaginary part is the most natural place to store information, because fluctuations and control, at least the control part works on the real part. So this is sort of taken. That is taken just to make sure things don't explode. The imaginary part is less constrained. Now, this sort of weird reasoning is a very general one. I didn't even say what is homeostasis or what is noise. I didn't say anything. So maybe any homeostatic mechanism that I can think of will conform to this intuition. So we can try a few. The simplest one is dissipation. Well, if the fluctuation is unchecked, things explode. So let's just have a restrictive force that pushes them back to 0. Subtitles again. The fluctuation term has noise and just something that pushes it back to 0. That's one option. Another is rate control, also known as synaptic scaling. So this means that neurons want to fire at a certain rate. They want to fire at 5 hertz, roughly. And if they fire a bit less, then they try to upscale their synaptic input, and if they fire more, they try to downscale their synaptic input. And this will overall lead to the overall effect will be that neural activity does not explode because it tries to get to a certain reasonable range. And again, subtitles, which are a bit more messy here, but basically you have a target firing rate, and so again, same noise, but the difference between the current rate and the target rate determines the plasticity. You also need to add another term to make this stable. And another one which is completely different, inspired by work from Magnesco, is decorrelation. So this means that if one particular type of instability is that activity becomes highly correlated. So all the neurons sort of do the same thing, and then the synapses maybe even accelerate this, and the entire activity becomes locked to sort of one mode. But if you want to make things less like, like a population spike of a culture and more like a cortical desynchronized activity, then you can just put decorrelation as your homeostatic mechanism. And again, this can be done by just having a term which is a correlation term, basically. Okay. So now, these are three rather different rules, and now we want to put some memory and see how the rules affect this memory. Now, how do you put memories in eigenvalues? Because I just said two different stories. One was memory is how neural activity affects synapses, and the other was that there's this dynamical system thing of eigenvalues and real and imaginary. But there's a link between them. So the classic theoretical neuroscience account of memory, Hopfield, Hebb, and William James, and others before, the intuition is that when memory is recalled, then you have an ensemble of neurons that are co-active. And that is, that's what happens when you recall a memory, and that's also the memory. So the representation of a concept is an ensemble of neurons. How do you store this ensemble of neurons, this activity pattern in memory? Well, fire together, wire together. If two neurons are co-active in an ensemble, you want them to connect to each other. So basically, you want reciprocal connections within the ensemble. That will create a memory. That is exactly the Hopfield model, and it could be think as a result of Hebbian learning. Mathematically, this means that you have symmetric connectivity. Symmetric connectivity gives rise to real eigenvalues. And also, it's a low-rank creature, and it's an outer product. But basically, this concept of ensembles directly leads to real eigenvalues. So now we want to store memories. So you put memories in the connectivity. We have our connectivity, and we're going to add something to it. This is going to be the memory. Either in the real part, this is the Hopfield model, an outer product, this is symmetric, this is the reciprocal connections. Or something that looks quite artificial at this point, this is the simplest thing that can give an imaginary eigenvalue. Actually, it gives two imaginary eigenvalues, but a conjugate pair, but this is sort of the simplest mathematical construct, at this point, no biology, that can give me an imaginary memory. And now what happens to them? So memories here are these extra eigenvalues, real or imaginary. And now we're going to apply fluctuation and homeostasis. So dissipation, well, it brings all the weights to zero, and it erases everything. So no memory left, but that's kind of reasonable because we gave no room for any memory to reside. But that's, now once you have these other homeostatic rules, things are a bit different. So if you have synaptic scaling or the rate control, and if you put a memory in the real part, like the Hopfield model, and then you let fluctuations and homeostasis take place, this dies out very rapidly. If, however, you put a memory in the imaginary component, you see that it hardly moves. I mean, it sometimes does decline a bit, but it hardly changes at all. And if you have this decorrelation rule, which is a very, very different creature, you can also look from the noisy version of it. It's a very different mathematical creature and a very different mechanism. Again, the real memory dies out immediately, whereas the imaginary one lasts for a very, very long time. Again, this is what we expected just from thinking about real and imaginary values and the fact that homeostasis has to control the real part, but shouldn't necessarily care about the imaginary one. So, imaginary is, a weird word. So is storing information in the imaginary part of a spectrum an imaginary concept, a mathematical one, or does it have any relation to biology whatsoever? So how can, so far what I did was just say, well, here's a mathematical construct that puts something in the imaginary eigenvalue. Yeah, nice, but how can you do that? Well, actually, there's well-studied biological phenomena called spike time-independent plasticity, which is temporally asymmetric, right? So the presynaptic and postsynaptic spikes, if they're like this or like that, it changes the sign of the connectivity. If you translate that to a rate model, this results in an anti-symmetric term, which is very similar to the mathematical construct I put in hand to apply an imaginary eigenvalue. So if we put the rate implementation of STDP, and now we take our network and we give it some input pattern, it's going to be in some trajectory in a two-dimensional plane. Then what we see, now we're going to track the imaginary eigenvalues, and after we put the stimulus, indeed we see that an outlier, sort of a pair of eigenvalues representing the memory arises. We can also correlate it and see that indeed the eigenvectors associated with it are really the ones that belong to the input I chose. And we can also later apply a second memory, and we see that they co-reside without interfering with each other. So this means that homeostasis implies imaginary coded memories are more resilient than real coded memories. It's not completely an imaginary concept because STDP can create such memories, but what is an imaginary coded memory? What does it, how do you interpret that? So actually it's a simple extension to the Hopfield model. So a single memory is going to have this form, which is sort of this anti-symmetric term, which is actually just like the Hopfield model, only you replace a fixed point with a limit cycle. So instead of having the Hopfield model, the whole point is a fixed point, it's an attractor. So you give a Q, let's say a partial version or a corrupted version of your memory, and the dynamics will converge to the same thing you stored in memory and will stay there forever. That's why persistent firing was linked to the Hopfield model. In this case, again, we have associative recall. So if we have, I think, 10 memories in the network, and we give a Q that is just a bit similar to one of them, the network will converge to a state that is highly similar. This is pattern completion. It will complete the memory to the original one, but the dynamics will not be a fixed point, but will be an oscillation, a limit cycle. And again, we can have sort of a Hopfield of limit cycles. So instead of having many fixed points, we now have many limit cycles. Similar capacity, there's a factor of 2 because now we have 2 vectors for every memory. But we have associative recall, and the memories are now going to be limit cycles instead of fixed points. So putting all of this together, we see the following. We have we now have 3 different memories. And we're going to present a transient input. Okay, so sorry. This is time, and these are the overlaps or the projections or readouts of 3 different patterns. So this is asking how much the neural activity resembles pattern 1, 2, or 3. And now I provide pattern 1 as an input, which obviously leads to the activity resembling pattern 1, and that's it. Things go back to baseline. Then I give an input of pattern 2, and I never give an input of pattern 3. It's a control. Later on, I give a short retrieval cue. And again, this can also be a partial cue because we'll have pattern completion. And I see that this cue is highly amplified. And I give another cue. And if I give a cue of the same magnitude, but to a pattern that was not encoded, then I don't have anything. And once more, because the memories are limit cycles, then the retrieval is an oscillatory pattern. And throughout the entire duration of this simulation, synapses are always moving. Okay, so all the time there is activity-independent fluctuations. There are activity-independent fluctuations in all the synapses without any constraints. Only homeostasis works to keep this from diverging. Another thing we can do is sort of quantify this. Of course, so there are activity-dependent fluctuations and activity-independent fluctuations. Homeostasis, for instance, is an activity-dependent fluctuation. Okay? It's not learning-related, but it's activity-dependent. So we can quantify the activity-dependent and activity-independent parts and see they are of similar magnitude. Again, similar to what has been observed in the experiments. And finally, at this point, I would say it's highly speculative, but if indeed, again, just saying that homeostasis has to work more on the real part, therefore you need to store information in the imaginary, therefore memory should be recalled in an oscillatory manner, then we should look for oscillations during memory recall. Now, there have been quite a few works that showed correlations between e.g. Oscillatory activity and work in memory and the quality of recall. So here we have sort of in the model, you can see that, again, it's not a big surprise. So yes, you have some oscillatory activity in retrieval relative to rest, but that's just showing this thing in a different way. The more speculative part is the following. The size of these imaginary eigenvalues, their distance from the origin, encodes 2 different properties. One is the strength of the memory. If it is more separated, it is stronger. It will take it more time to decay. The other is the frequency. So the size of these imaginary components is highly correlated to the frequency of oscillation. So in principle, if you have a given memory, and then over time this memory erodes a bit, as it erodes, the retrieval of that memory should also change to a slower frequency, to a lower frequency. And we do see this effect in the model, but while we wanted to have a nice, clear correlation with all the colors on top of each other, we do not. So at least in our model, this effect, while it exists, the variability of the effect is smaller than the variability between different items. Now, maybe this is general, maybe it's just the way we implemented it with highly implausible rate neurons and many other assumptions. But in principle, if you could somehow limit to the same item at least, there should be a correlation between the frequency and the resilience of a memory. Okay. So, it's possible to store memories despite strong ongoing synaptic fluctuations. Here we propose to do this at the network level. And the specific segregation we proposed is between imaginary and real coded memories. Now, there were other suggestions of segregations for inhibitory and excitatory and many other, and also for dynamics on functional and degenerate axes. So in a sense, this is another one, but in a sense, it stems from very general arguments on stability. Now, it turns out that STDP and homeostasis naturally follow such a segregation. And the consequence of that is that the natural dynamical unit for memory is a limit cycle and not a fixed point attractor. And